Now the question is, the temperature of glass vessel containing 100 centimeter cube of mercury is raised from 10 degrees Celsius to 100 degrees Celsius. Calculate the apparent cubic expansion of the mercury. So real cubic expansivity of mercury is 1.8 times 10 raised to power minus 4, and cubic expansivity of glass is 2.4 times 10 raised to power minus 5 per Kelvin. Now there are some things you have to understand about real and apparent expansivity first. So now let's say we have a vessel, like a glass vessel like this. Now you fill the vessel with liquid. So let's say we fill the vessel with liquid. Let's say mercury is inside the vessel. So let's say this is the level of the mercury. See the blue, the highest level of the mercury. So let's call that point A. So let's say this is the level of the mercury, A, this point. So now this is the vessel or glass. So that is glass vessel according to the question. So this is the glass vessel, and what you have inside is the mercury. So that is the liquid inside. So now the liquid, the highest level it reaches, A, naturally. So this is what we have. We have a glass vessel and we have mercury inside, and this is the level of the mercury, A. Now this mercury is subjected to heat, so we heat the mercury. Let's say this is it. So we heat the mercury. Now as you heat the mercury, then the vessel will expand. As you heat this mercury, the vessel will expand. As in, this vessel will expand if you heat the mercury. So now as the vessel expands, then the liquid, the mercury inside this vessel will reduce, because if the vessel expands, then the mercury will reduce to a certain level like this. It will reduce to a certain level. Yeah, so let's call this point B. So remember, this is the initial level of the mercury, but if you now set the mercury, like if it's subjected to heat, then the level of this mercury will come down to this point B. Now after some times, if the heating continues, then the mercury will rise again. Then it will rise to a point. Let's call this point C. So the mercury will rise to a point there again. What do you notice here? In real life, if we have a vessel in real life like this, and the level of the liquid is here, if you should set this on it, like this vessel, if it's set on it now, that means the mercury will only increase from here to here. You will not see the vessel expanding, and you will not see the mercury going down first before increasing in real life. So but practically, so this is what will happen. The vessel will expand and the liquid will go down first, and after sometimes it will increase. Now because in real life we are not going to see the vessel expanding, the only thing we will see is that the liquid just rise from A to C. That means A to C is called the apparent expansion. So apparent expansivity. Apparent expansivity is AC. That is from A to C. The liquid will go there directly in real life. That is apparent expansivity. Now, real expansivity. will be equals to BC. That is, it is from B. Remember, if you subject this vessel to it, the normal level of your mercury will first reduce to this yellow. From here it will go to the red. The real expansion is from this yellow to red, but you won't see it in real life. In real life, you will just see that it's moved from A to C. So now that means the real expansion is from B to C. And what caused that real expansion? So we have the expansion of vessel, expansivity of glass vessel. So expansivity of glass vessel is AB, because as the glass vessel expand, the level of the liquid reduce from A to B before rising from B to C. So B to C is now the real expansion, while the apparent, what you can only see in real life, that is without considering the expansion of this glass vessel, without considering the expansion of the glass vessel, then the expansion will just be from A to C. That is apparent expansion. Now, but the expansion of glass vessel is from A to B. That is when the liquids reduce. So if you combine these three now, it means real real expansivity will be equal to, so that is real expansivity is equals to expansion of vessel, so expansion of glass vessel plus expansion plus apparent expansivity. So that is real expansivity, which is BC, that is from B to C, is equals to expansion of vessel, that is AB, plus expansion of the apparent expansivity, what we can just see without the expansion of vessel, is AB. AC, that is from A to C, is apparent expansivity. Now, the representation of cubic or real or apparent expansivity, we use gamma. So now remember, we are talking about volume, and volume expansivity is gamma, which is change in volume over original volume, let's call it V1, times change in temperature. So now this change in volume, if you cross multiply, is gamma V1 then change in theta. So this is now formula for change in volume. So now that is volume expansion. So now real expansivity now will be equals to gamma R. So I'm representing this gamma R now as real expansivity, then V1 change in temperature is equals to, remember they are set into the same temperature, that it is the same for all. So now equals to AB. You know, AB is the expansion of vessel. So expansion of vessel, that means gamma expansion of vessel V1 theta V1 theta plus AC. From A to C is apparent. So apparent expansivity too will be, I'll use A, then V1 change in theta. Here too is change in theta. So V1 change in theta will be common to the 3. Then it will remain this, this, and this. So generally now it will remain real expansivity is equals to the expansion of vessel, that is expansion of glass vessel, plus apparent expansivity. We use it that way. So now that is what we have in this. So now from the question, we already have data given. So in the question, the temperature of a glass vessel containing 100 centimeter cube of mercury, so that is V1, volume of mercury, that is 1000 centimeter cube. Again, is raised to 10 degrees C. That means theta 1 is equals to 10 degrees C. To 100 degrees C, that means theta 2 is equals to 100 degrees C. So calculate the apparent cubic expansion of the mercury. So real cubic expansivity of mercury is real expansivity of mercury is 1.8 times 10 raised to power minus 4 per Kelvin. Remember, as I show you in the diagram, that is, the level of the liquid is here, it dropped to B, and from B it increased to C. So the real expansion of this mercury is from B to C. So we are given that real expansivity of mercury, so from B to C. So the apparent the cubic expansivity of glass, remember the glass will first expand if it's subjected to it, and the level will reduce from A to B. That one is called the expansion of glass. So we have that also. So expansion of cubic expansivity of glass, so that is glass vessel, so just like the way I write vessel here, of glass vessel is equals to 2.4 times 10 raised to power minus 5 per Kelvin. Now, from this relation, we can know our apparent expansivity there. So that is, from real expansivity is equals to expansivity of glass plus then apparent expansivity. So now, real cubic expansivity of the mercury is 1.8 times 10 raised to power minus 4 equals to the expansion of the glass, that is cubic expansivity of glass, 2.4 times 10 raised to power minus 5 per Kelvin. So I'm removing the units. But please take notes of something here. This is there is a mistake here. This is 1.82. There is 2 here. 1.82 times, take note. So that means there is 2 there, 1.82. So in the correct question there is 2. So 1.82 times 10 raised to power minus 4. So remember, real cubic expansivity of mercury can just be 1.82 8 normal, but based on this question it is 1.82 that we have there, so there is error there. So if it is 1.8 you have used, but now I'm using 1.82 according to this question. There is a mistake there, so 1.82, take note, plus the apparent expansivity of mercury. So now collect like terms. So that means this one, the apparent expansivity will be 1.82 times 10 raised to power minus 4 minus 2.4 times 10 raised to power minus 5. So now the apparent expansivity now is, so press your calculator. So if you press 1.82 minus 2.4 like that, so everything will give you 1.58 times 10 raised to power minus 4 per Kelvin. So now this is the apparent expansivity. So now, but what we want to find is the apparent cubic expansion, not the apparent expansivity. So now, to find the apparent cubic expansion, we have 3 formulas depend on the information given. So let's take note of this value. So let me clear this place. So let's take note of this value now. So we have 3 formulas that we can relate here. First, know that it depends on your question. This apparent expansivity can be apparent increase in volume divided by original volume. Remember, our original volume here is 100, is given here, times rise in temperature. Rise in temperature, or apparent expansivity can be mass of liquid expelled. So if there is any liquid that escape the vessel, mass of the liquid expelled over mass of liquid remain. Mass of liquid remain times rise in temperature, or the apparent expansivity can also be volume of liquids expelled divided by volume of liquid remaining. Volume of liquid remaining times rise in temperature. So but in this our question, there is no mass that is expelled. The only thing we have here is increase in volume, and that is apparent increase in volume. So according to the question, there is nothing like a mass is expelled, that is no mass, no liquid is escaped from the vessel. So assume liquid escape, the question should mention it. So but here we only have apparent increase, so we are using this relation, this formula. So that means apparent expansivity is equals to apparent increase in volume. So I'll just represent that as change in V, increase in volume, over original volume V1 times temperature rise, that is theta 2 minus theta 1. So I have already know my apparent expansivity, which is this. And take note of when to use any of those formula. I'm using this because no liquid is expelled, so it's just increased. So now this will be 1.58 times 10 raised to power minus 4. So that is apparent increase in volume. So we are looking for this divided by original volume 100 times temperature rise, that is 100 minus 10. So we have it T1, theta 1 and theta 2. So this is theta 2 minus theta 1. So now this is 1.58 times 10 raised to power minus 4 equals apparent increase in volume over 100 times 90. So now 1.58 times 10 raised to power minus 4, apparent increase in volume divided by 9,000. Remember this is over 1, so we cross multiply. So if we cross multiply, we are going to have so if we cross multiply, we have apparent increase in volume is equals to 1.58 times 10 raised to power minus 4 times 9,000. So press your calculator. So what do you get in the final answer? So apparent increase in volume will give you 1.422, so centimeter cube. So that is the final answer. Take note of the right time to use the formula. Here the question did not say any liquid expel, or so if there is liquid expel, so we have the remaining. But here if there is only increase, that is when the bottle is subjected to it, the liquid just increase, no liquid leave this, as in no liquid expel, no liquid escape, to just increase. So if it's expelled, the question will tell us how many liquid expelled, so we can find remaining or like that. So the answer here is now 1.422. So study the three relation. So